Today, let's take a look at linear systems. Hopefully, systems sounds familiar. You did learn systems extensively in eighth grade math. You learned how to solve them algebraically, graph them. And so, here at the top, the definition a system of linear equations is a set of two or more equations. Their solution to any system is a set of ordered pairs that makes both equations true. So, one method for solving a system is to graph both equations and find the intersection point. Because if I graph line A and I graph line B, the point that they share in common would be the ordered pair that would make both equations true. It would be a point along each of those lines and therefore fit both equations. So we're going to practice that again. You did it in eighth grade math. We've been working with linear equations, graphing slope, and things like that lately. And so hopefully this will be a breeze. And then we'll look at algebraically how to solve systems below. The first one, the top equation says y equals negative x plus 6. I'm going to make some notes here. It is in slope intercept form, so I can see that my slope is a negative 1. So when I go to graph that, that's going to be down 1 over 1. And then my y-intercept is 6. So let me go and start graphing that. Starting with that y-intercept, plot a positive 6, and then use your slope down 1 over 1. Down 1 over 1. Now, what did I say? We were graphing lines to find their intersection point. So I'm going to need to make this very long. So because I don't know where it's going to intersect, it might be way down here. It even could be up at the top. So I'm going to go up and left, still making that negative 1 slope. Notice my line is going down from left to right. If I drew a capital letter N, it would have the same slanty part of that letter. The second equation I'll do in a different color. Our slope, this second equation, y equals 1/4 x minus 4, is also in slope intercept form. The slope being 1/4. The y-intercept is negative 4. I'm going to start with that y-intercept of negative 4, plotting that on my y-axis down there. From there, go up 1 over 1, 2, 3, 4. Positive 1/4 slope. Do it again. Up 1, 1, 2, 3. There we go. Now, I like my lines to have multiple points so I can draw a nice straight line. So I'm going to go down and left 1, 2, 3, 4 from that y-intercept to make some more points. 1, 2, 3, 4. And now I can make a beautiful straight line. But we were looking for the intersection point, the place that they shared in common, and that was right here. That is my solution, the intersection. And we are going to label that ordered pair. That is 8, negative 2. 8, negative 2. So make sure you carefully label that. Some students get their x's and y's flip-flopped. 8, negative 2 is our intersection point. Therefore, our answer to our system, because the ordered pair 8, negative 2 would make both equations true. If I plug in 8 for x in either of those equations, when I simplify, it'll be equal to our y value, negative 2. Really cool. Let's try again. Number 2, y equals x plus 8. That's also in slope-intercept form. Our slope here is an understood 1, so I'll have up 1 over 1. Our y-intercept is 8. So starting at 8 on my y-axis, plot that y-intercept and make a positive up 1 to the right 1 slope. Now, it might not intersect up there. So let me make some more points down and to the left. I'm going to go down and left. Negative, down, negative, left. 2 negative movements to continue that positive slope. And we're just going all the way down here, making a nice straight line. And let's look at our next equation. Oh, 2x plus y equals negative 1. That's not in slope-intercept form. It's in standard form. You could identify that the y-intercept is at negative 1 because it's in that standard form. But you might want to actually just change it to slope-intercept form. That wouldn't be too hard here. Subtracting 2x to the other side will give us y equals negative 2x minus 1. And now it's in slope-intercept form. No big deal. If there was a coefficient in front of y, I would also divide everything by y, possibly giving me some fractions. for our slope and things like that. Y equals negative 2x minus 1. My slope's negative 2. Y-intercept is negative 1. We're going to start at negative 1 on the y-axis and plot that y-intercept. Then our slope is negative 2, or negative 2 over 1 is probably what I should have written to have our rise and run as a fraction, going down 1, 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. But I can see that I need to graph above, right? 1, 2, left, 1, 2, left, 1, 2, left. That's where it's going to intersect. I know my line's not exactly there, but that is going to be our intersection point. Try to draw this one a little bit straighter. All right, let's label that ordered pair. Again, it is right there despite my crooked line. Our intersection point, our solution, is at, that's negative 3, 5. Hopefully your line is actually straight and looks a lot better. So negative 3, 5, both equations share that ordered pair on their graphs. Therefore, if I plug them into the equation, they would make both equations true. When I plug in negative 3 for x, the y value would be 5. Or in our bottom equation, when I plug in negative 3 for x and 5 for y, it equals negative 1. How about that? So that's how you solve a system, by graphing, like visually looking at our system on the graph and their physical intersection point. You can also solve systems algebraically without a graph, because sometimes they're cumbersome. Sometimes they don't graph very easily. Sometimes you don't have graph paper in your pocket or your graphing calculator in your hand. So there are algebraic methods. Hopefully, again, this is a review from 8th grade math. The first method that we're going to review is substitution. The notes here says another method for solving systems of equations is the substitution method, in which one equation is solved for one of the variables, and then that expression from that first equation is plugged in or substituted into the other equation. It gets its name because we're substituting. We're replacing one of the letters in an equation with the expression from the other. So let's look at the example I have to the right. This is a system suggests using substitution. The top equation says y equals negative 10x plus 9. And the bottom equation says 2x minus 10y equals 12. The top equation. I think we get so used to seeing y equals equations, we kind of forget what that means. It's saying that y is equal to, it is the same thing as negative 10x plus 9. They are exactly the same. They are equivalent. So I'm going to use that statement to replace y in the second equation with negative 10x plus 9. I'm going to plug that all in right there. So my second equation is going to look like 2x minus 10, and I'm going to use parentheses to show I'm replacing y with negative 10x plus 9 equals 12. It's just like if I had told you in the top equation y equals 3, and then plug it into that second equation. You would just plug in 3. But instead, it's not just 3, it's negative 10x plus 9. So from here, notice our equation now just has x's. So I can do distributive property and combine like terms and solve for x and get halfway to our ordered pair answer. So I'm going to do that distributive property across those parentheses. Negative 10 times negative 10x is going to give us 100x. And then minus 90 equals 12. We have like terms with the 2x, and the 100x gives us 102x. Minus 90 equals 12. This is a two-step equation. Add 90 to both sides so that you have a 102x equals, guess what 12 plus 90 is? 102. Divide both sides by 102 to completely solve for x equals 1. Okay, now the answer to a system is the ordered pair that both equations share, that they have in common. So our answer is an ordered pair, and so far I have that x is 1. Oh, Miss Brian, there's more. It's okay. It's okay. From here, it's not too bad. I'm going to use that top equation that says y is equal to negative 10x plus 9 to help me figure out what y is equal to. Negative 10 times x. I just found that x is 1 plus 9. Y is equal to negative 10 plus 9 or negative 1. Using that top equation, we just found out what y was. It wasn't a huge deal. So that substitution, our final answer, the answer to this system, the ordered pair that both equations share, is 1, negative 1. If I plug in 1 for x, the y value would be negative 1 to make that equation true. Both of them. Yes? Okay, substitution. You are literally substituting one of the equations into the other to help you solve for a variable, and then you use that information to solve for the second. Another algebraic method is called elimination. Elimination can be used to solve a system of equations. Two equations are combined to yield a third equation. The elimination method creates like terms that you can add to make 0. Elimination method. In elimination, we are going to eliminate one of our variables by manipulating our equations so we get like terms. Then I'm going to add straight down. Maybe you remember that from 8th grade, adding straight down, and where they're like terms, they have opposite signs that make 0. So look at our system, our example to the right. 8x plus 4y equals negative 4 is our top equation. Bottom equation, negative 4x minus 5y equals 11. If I add right now, I'm not going to get anywhere adding my like term straight down. 8x plus negative 4x is 4x. 4y minus 5y, negative 1y equals, what is that, 7? Not getting anywhere. Now, here's the thing. With equations, you can, I'm going to make a note over here on the left, you can multiply the entire equation, and that's important, entire equation by any number. You're allowed to do that. You're allowed to take a equation and multiply every term, every piece of that equation by the same number. So like if I multiplied it by 2, if I doubled every piece of that equation, well, that would just make the left side twice as big and the right side twice as big, and therefore still equal, still balanced. So maybe not 2, but we're going to see, what should I multiply one of my equations by so that I get opposite values, opposite coefficients on one of my variables. You know where my eye is drawn to? Those x's. I've got 8x in the top and negative 4x on the bottom. Is there any way I can make that bottom negative 4x into a negative 8x? Because if it was 8x and negative 8x, that would make 0. So surprisingly enough, yes, I'm going to multiply that bottom equation by 2. I'm going to make it twice as big. Now, I'm leaving the top equation alone. So I'm going to copy it here to the side. And the bottom equation, like I said, I'm going to multiply everything. You got to multiply everything or our equation is no longer balanced and we broke the rules. So 2 times the negative 4x, negative 8x, what I want. Then also everything else. 2 times negative 5y makes negative 10y equals 2 times 11. A lot of students will forget the last one. Make sure you go all the way across our equation. Now, I'm going to make like a big addition problem and add straight down. That 8 plus negative 8 made 0. Those are gone. Yes. No more x's. Now it's only going to be y's. 4y plus a negative 10y makes negative 6y. And negative 4 plus 22 is going to give me 18. Look at this little baby equation. Negative 6y equals 18. Divide by negative 6 on both sides so that you can see y equals negative 3. Now, the whole point, what we were trying to do is find our intersection point, or the ordered pair that both equations share. So now I know that y is negative 3. That's the first part I got, was y. So we did a little bit of multiplication to one of our equations. So we would have opposite coefficients that would make 0 on one of our letters. Now I'm going to take that -3 that I got for y and plug it into one of my equations. It doesn't matter which one. You can choose top, you can choose bottom. I think I'm going to choose top because there's less negatives. If you want to use the bottom, you'll be fine. So let's see. 8x plus 4y. I know y is -3 equals -4. Let me evaluate. 8x, 4 times -3 is going to give me -12 equals -4. And now look, it's a little two-step equation to help us solve for x. I'm going to add 12 to both sides. 8x equals 8. Divide by 8 on both sides. X equals 1. Final answer. The ordered pair that both of those equations have in common is 1, -3. I'm going to plug in 1 for x, -3 for y. It would make both of these equations true. So there is my answer using the elimination method. We multiplied one of our equations. Sometimes you have to multiply both. That's when it's really messy. To make opposite coefficients that when I add straight down, it makes x into 0 or y into 0. It doesn't matter which. On this example, if I wanted to eliminate the y's because it's a 4y and a -5y in our original problem, I would have to multiply both equations to maybe make it like 20. So like the top, multiply it by a 5, the bottom, multiply it by a 4, so it makes 20 y's. And so that sounds like a lot of mess, but it is a possible solution path. So there was a review of 8th grade math systems. We graphed them, we solved them algebraically using substitution and elimination. And while systems are still an important concept in Algebra 1, it's not as big of a concept. So I want to be sure that you know how to use your tools on your calculator. Now you can still physically graph them. You can still use substitution and elimination. So if you prefer solving by hand, you can do that. Or if you don't have a calculator in your hand, that's what you can do, substitution or elimination. But I want to show you, if you do have the Inspire calculator in your hand, how you can solve your systems of equations using your calculator. It's a wonderful tool. Probably if you don't have the Inspire at this point, after I show you this, you will really want it. So your calculator, I've got it pulled up, probably looks like this when you turn it on, Scratchpad or a document. Scratchpad, weird things happen. It bogs down our memory. It's a little bit harder to clear off our scratch work as we work on Scratchpad. So try not to use Scratchpad. Biggest recommendation. Always use a new document. If you have anything on your screen, it's going to ask you if you want to save. Nah. And we are going to add a calculator, a little calculator page. Looking at my steps on my notes here. We're going to go, once you have a calculator page open, even if you do some calculations, maybe 4 times 3 or something, if you have anything on there, that's okay. I'm going to do menu. Algebra is number 3. Good way to remember this is you are in algebra class. And then the second option here is solve a system of linear equations, which is exactly what we are doing. We are solving linear equations. They graph lines. They are just x and y. There's no exponents or radicals or crazy things. They are linear and they are equations. So solve system of linear equations. You get this little pop-up box that asks the number of equations, 2. It's going to default to 2 every time we are solving systems of 2 equations, variables x and y. Beautiful. Now to get down to OK, if you arrow down, it's going to start changing that number from 2 to 1. You see that? So make sure you leave that at 2. So how do you get down there? You can use the tab button over here and tab down to OK and hit enter. All right, number 3 on our notes, I'm going to type that in. Notice my calculator says lin solve, like linear solve, and it gave me 2 little boxes to put each of my equations. Do you see that? How great is that? So on number 3 from our notes, I'm going to type y equals -6x plus 8. I'm going to arrow down to go into the bottom box so I can type 7x plus 2y equals -14. Okay, include the equals. Some students forget to put the equals in the last part of the equation. Entire equation, including the equal sign, exactly like you see it, okay? Then, big thing right here, hit enter. And voila, the answer is 6, negative 28. Ta-da! How great is that? So when we are in a test setting and you are crunched for time where you could possibly make arithmetic mistakes along the way, you have this lovely function on the Inspire calculator. 6, negative 28. I'm going to make a note here on our notes that we use the calculator. And we got 6, negative 28 as our answer, where 6 is x and negative 28 is our y value. Sometimes on test questions, they will ask just what is the x value or just what is the y value. So just make sure you recognize on the calculator, it does show us in order of x, comma, y. I'm going to do the same thing for number 4. I've already got stuff on my calculator page, and that's okay. Go ahead and hit menu, algebra. You can also just hit the number keys on your keypad. So it was menu. I'm going to do 3, 2. Tab, okay. And I'm ready to type it in. 10x plus y equals 4, arrowing down. So I can put in negative 5x minus 5y equals 25 and enter. 1, negative 6. One, negative 6, where x was 1, y was negative 6. How about that? I didn't have to use substitution. I didn't have to use elimination. I typed it in my calculator, and it gave me the answer. So hopefully in 8th grade math, you learned your strategies. Now we are utilizing technology where we can. Enjoy that feature. The last part here is determining whether the linear system has no solutions, infinitely many solutions, or one solution. So I'm going to utilize the calculator again to do this. Instead of having to solve and find out or manipulate my equations to find out, I'm going to use the calculator. Once again, I'm going to do menu, 3, 2, tab, okay. I've got my 2 boxes to type in. 3x plus 4y equals 3. Arrow down, negative 12x minus 16y equals negative 9. And enter. No solution found. Boom. No solution. So once again, we used the calculator. And we got no solution. Now, what does that mean? No solution. Well, there is no ordered pair that they share in common. But let's also review from 8th grade math graphically what would that look like. So I'm going to I'm going to add another page here. So if you see at the top of my screen, I've got 1.1. That's like my first tab of my calculator screen. You can add another tab, like another page here, if you do Control I, like insert. Control I is going to open up another page, and it's asking, do I want a calculator page or a graphing page? I'm in a graph. I'm going to go ahead and change it to relations because these equations are not y equals. So menu, graph entry edit, and change it to number 2, a relation. So I can type in the equation however it looks. It doesn't have to be in slope intercept form. Our top equation was 3x plus 4y equals 3. I'm going to arrow down for a second relation. It already graphed my first equation there. Negative 12x minus 16y equals negative 9, and I'm going to hit enter. I've got a blue and red line graphed there. And right now they look like they are practically on top of each other. Let's zoom in. If you go menu, you have number 4 is window zoom, and you can zoom in number 3. And you can move your cursor to where you want to center that zoom. So when I first pulled up my cursor, it was way up here in the corner. I really don't want my zoom to focus over there. I need it to focus closer to these lines. So let me bring my cursor close over here, and I'm going to hit enter. I can even adjust it a little bit more and hit enter. Every time I hit enter, it's going to zoom in. Yes. Okay, so they did look like the blue and red lines were like on top of each other, but now you can totally see that they are parallel. Let me kind of sketch that for us on our notes. They were parallel lines. And that's why there's no solution. There's not going to ever be an intersection point because they have the same slope, the same steepness. They'll never cross like railroad tracks. And so no solution for this system. All right, let's do the same thing for number 6. I'm going to use the solve systems tools on the main page. I'm going to go back to 1.1, my other tab on my calculator. I'm going to do control and arrow left. Takes me back to that calculator page. How neat is that? All right, so I'm going to type in menu, algebra, linear solve, 2 equations, okie doke, x plus 2y equals 5, arrowing down, 2x plus y equals 12, and enter. 19 thirds and negative 2 thirds. That's a messy answer, but it is correct. You can double check our equations, make sure you typed them in, but that is the answer, the solution. So to answer this question, it has one solution. There is a solution. So like we did before, let's go and see what it looks like on the graphs. I'm going to go back to that calculator graph tab, my 1.2, doing the same thing. I'm going to do control to the right to take me to 1.2. And I'm going to change my equations here. To open your equations box, hit tab and arrow up to the first one. I'm going to do control delete key, which is clear, control clear. To clear it all out, I'm going to type my top equation, x plus 2y equals 5. Arrowing down, I need to clear this one off. Control clear and type the new second equation, 2x plus y equals 12. Enter. Oh, where'd they go? Well, remember I zoomed in. So let's zoom back out. In fact, hit menu. Under zoom, there is a zoom standard, number 5. Like put it back into a standard view, like the regular view. Okay, so it takes you back to like that very original spacing on your graph there. And you can see our red and our blue line are crossing somewhere down there in the 4th quadrant. I'm going to sketch that on our notes for us. They're crossing something like this. Probably not very accurate, but there is one solution, one intersection point. And we're going to do the same thing for number 7. I'm going to go control left to go back to my little calculator tab here. Menu 3, 2, tab, okay. And we've got 2x plus 3y equals negative 6, arrowing down for x plus 6y equals negative 12. Enter. What's that? Negative 3 times c1 over 2 minus 3, c1. That's weird. We use the calculator. And it said negative 3 times c1 over 2 minus 3 comma c1. What in the world? This represents many solutions. So on the calculator, if it pops out C1s anywhere in your answer, then you know it is a infinitely many solutions equation. What's happening here? So your infinitely many solutions are when your 2 lines are exactly the same. They share every point in common, but it's only every point in common along that line. So when we say infinitely many solutions, we don't mean just like any old ordered pair on the coordinate plane. It's got to be a point along that line. Both lines share those ordered pairs. So it's not everything, only the things that they share in common. So what the calculator has done has written our ordered pair in terms of the y value. Do you see how it wrote the y value as C1? And then our x value is -3 times that C1 value, the y value, divided by 2, then -3. So it's trying to explain the best a calculator can that there are ordered pairs in common, but it's got to be in terms of that linear line. Let's graph it and show you. I'm going to do control to the right to go back to our graph page. I'm going to hit tab and arrow up to my first relation. I'm going to hit control clear, retype our new first equation, 2x plus 3y equals -6. Arrowing down, I need to write my new second equation, control clear, 4x plus 6y equals -12. And now this one, maybe you remember what it looked like on number 5. This one, literally red and blue are on top of each other. I can't even see really the blue line anymore. If you want to do menu, window zoom, and zoom in, and try to see if we can get any closer. Is it going to be, I just keep zooming in and I don't see any blue line. The blue and red line are literally on top of each other. I'm going to reset my window here to standard. They are exactly the same line. So let me sketch that for our notes. They are literally the same line. Finishing up these notes, this last part, when two functions such as f of x and g of x are set equal to each other and the resulting equation is solved, the solutions to that equation are represented by the x coordinates of the points of intersection. So we're going to be using that same concept we've just been working on with the systems. Now we'll see it being used in a variables on both sides equation kind of format, and we're just concerned with that x coordinate of our intersection. So number 8, in order to solve the equation -2x minus 10 equals 2/3 times the quantity x plus 1. That's an ugly equation, right? The student graphs two linear functions. F of x equals -2x minus 10. That's the left side of the equation. And g of x equals 2/3 times the quantity x plus 1. That's the right side of our equation. So they graphed it, and you see there they've got two lines. The question at the bottom, what is the solution to that equation? So what the student did is completely legal. You can absolutely graph each side separately and see where they intersect. This intersection point is going to help us identify our solution. That intersection point is -4, -2. And I only care about the x value. When x is -4, it will make this equation true. It'll make both sides equal because physically on the graph, they share that point of intersection. In our equation, we only have x values that we're trying to plug in to make it equal. -4 is going to make that happen because they literally share that place on the graph. -4 is our solution. Number 9, in order to solve the equation 2x plus 7 equals -x plus 1, we have a typo there, sorry about that. A student graphs each of those separately. F of x as the left side, 2x plus 7, the right side as -x plus 1, which is 2x plus 7 is the left side, -x plus 1 is the right side. So what is the solution to the equation of f of x equals g of x? So we can still use the calculator and what you've been using solving systems. So let's grab the calculator, and I'm going to use the solve system function. So on my calculator, new document, going to the calculator page because we are going to go menu, algebra, solve systems of linear equations. We've got 2, tab to OK. This is my system. Now careful because f of x represents y. I'm going to type in y equals 2x plus 7 as my top equation and y equals -x plus 1 as my bottom equation. Y equals 2x plus 7, and arrow down, y equals -x plus 1. And enter. Our intersection point, if this was a system, is -2, 3. and that x value is my solution. When x is -2, this equation would be equal, because I'll be plugging in, let me use a different color, plugging in our x's right there, and that would make our both sides of our equation equal, because in fact, both sides will be equal to 3. So just piggybacking off what we've been talking about systems, this is another standard that comes up, and I just want to make sure we emphasize that. So linear systems, you can graph them to visually see where they share an ordered pair, their intersection point. You can use substitution or elimination as algebraic methods, but we also have this fabulous tool on our calculator to help us work faster, smarter, better, using menu algebra, linear systems, and you write in your two equations and it will give you your answer. Try that. If you need a calculator, please let me know. I'll be glad to make sure that you get one. But it is definitely worth the investment to actually buy your own. You're going to use it Algebra 1, you're going to use it Algebra 2. You can use it when you take the ACT as a junior and senior. So it is worth an investment so you can have your own in your hands and you're not having to return it back to school or hope that you have one for the days that you might need it. So let me know if you have questions, guys. Happy solving your linear systems, and I'll see you in class.